Hello, do we have a Putnam 1985 problem? I'm too stupid for the newer ones. I'm sorry, I don't have time to crack problems lately because of school. So, we have the simple one. We have a unit circle defined by x squared plus y squared equals 1. We have a point P on its circumference, and we have a point Q inside of that circle. They're chosen uniformly. And with the diagonal PQ, we form a rectangle with sides parallel to x and y axis. And we have to find the probability that the entirety of rectangle is contained inside of the circle. So let's denote that P is defined by two coordinates, x0 and y0, and same deal with Q, but it's x1 and y1. Okay, cool. Now let's draw the circle. Let's go with the axis. Here and here. Let's choose an arbitrary point P, for example, here for now. And now let's observe how rectangles behave here. So, were to look at that, we keep the Q inside of the circle, then the issue caused is basically the issue of the other two corners. They are the impeccable ones, because if a side were to go outside, then so will the end of that side, because it's a straight line, and the end of that side is the vertex. P and Q are contained inside, so that vertex is gonna be one of the corners. Now, we were to look into those corners. Let's define them as C1 and C2, lying at points x0, y1, and x1, y0. Okay, and now let's write down a system. Actually, let's take a larger one to include the condition that we were given. For 1, x0 squared plus y0 squared is going to be equal to 1. x1 squared plus y1 squared is going to be less than 1. Now we have the corners have to make it so x0 squared plus y1 squared is less than 1. And the same deal but with this sort of symmetry thing, or with the x1 and the y0 less than 1. Okay, let's divide it from condition that we were given and condition that we're trying to satisfy. And let's take those inequalities outside to actually solve them in a matter. Okay. So, x0 squared plus y1 squared is less than 1, x1 squared plus y0 squared is less than 1. We can add, be it y0 squared or x0 squared, to get rid of the x or y terms. Work only with x0, x1, or only with y0, y1. So here we'll have 1 plus y1 squared is less than 1 plus y0 squared. And here we have a really similar case. x1 squared plus 1 is less than 1 plus x0 squared. Now we can subtract 1 from both sides, and we have y1 squared is less than y0 squared. And x1 squared is less than x0 squared. And now that's just about the absolute value of those. The value of y1 is going to be less than the absolute value of y0, and absolute value of x1 is going to be less than the absolute value of x0. So let's look into the implications on the circle. Let's begin by working with the fact that y1 is gonna be for sure less than y0, given that y0 is positive as for this point. So let's draw a line here, and same we can go for the x besides y. So we have these two lines. Now let's take the points of the intersection here and here. Circle is symmetric, so this part over here is going to be negative x0, y0, and this part is going to be x0, negative y0. And now in a similar manner, we know that x1 is going to be greater than minus x0. Let's take blue here. And y1 is going to be greater than minus y0. Again, the signs would be swapped if y0 happened to be negative or x0, but the signs would essentially remain the same. The shape would not change whatsoever. Okay, now we have used the color already, let's go with yellow. So essentially, what we deal with is this nice rectangle. And we can even find the area of it. And this rectangle is basically the places where Q can lie and form a rectangle with a P that will be entirely contained in the circle. So the chance for a given point P defined by x0 and y0 to lie inside of the circle is going to be the area of this rectangle, which is going to be just 4 areas of this tiny rectangle. So essentially 4 times the absolute value of x0 times y0 over the area of the circle. It's unit 1, so that's just going to be pi. Okay, cool. So that's essentially it. Now what we have to deal with is the rest. So let's begin. For one, okay, I'm kind of misled. Okay, no, never mind. Let's begin with the parameterization of x0 and y0, because having two variables is really inconvenient. And it's really easy to do because we're working in a circle. It's just going to be parameterization through the angle. We can take theta as arguments. This is going to be 4 times the absolute value of sine theta times cosine theta, where cosine theta represents x0 and y0 is getting represented by sine theta over pi. And that's gonna be 2 over pi times absolute value of sine 2 theta. And now interesting observation here. The maximum value of 2 times absolute value of sine 2 theta is going to be 2. Pi is greater than 2, so obviously it's going to be less than 1. So it can definitely work as a probability. I don't think I've made a mistake here. And now you have to consider, well, the entirety of circumference. We can't just work with a single point. So let's take some margin around P. And let's say that around it, the area of this huge rectangle is going to be approximately the same. So we can form a structure that's really close to Riemann sum. Let's say that we have, as for this step, the 2 over pi over n, where n is the amount of segments like this blue one. let's say that the length of one segment like that is going to be s again. It's the step, it's the length. Let's say that data I is going to be I times s. We begin with 0, so there's no need to specify that. Okay. And let's say that we can form a sum here. Say that it approaches infinity, n per se approaches infinity. We form a sum with that from I equals 1 to n. Now, for 1, we need the probability of a specific segment being chosen, which is going to be s over 2 pi. There's going to be 1 over n. 1 over n times then we have the probability, which is going to be 2 times absolute value of sine 2 theta over pi, because that's the probability that after we have chosen the thing. And now we need this weighting factor sort of thing. Wait a second, no, I'm being stupid, I think. Okay, wait a second, I'm having a brain freeze, I think. First we have the chance that this is getting selected, then this chance that this is getting selected. Okay, makes sense. Okay, I think I got it. So this is gonna be the expression overall. Now we need to put it in a form that would look like the Riemann sum. Now this over here is just gonna be pi of theta, so I think it will be convenient to rewrite it like that. Not pi of theta, p of theta. And for it to be a Riemann sum, the convenient way to go about it... Okay, wait a second, this is not gonna be just any... It's gonna be theta I, gonna be going up to 2 pi. So we have to get the step here. So what we're gonna do is just multiply this by 1 over 2 pi. And we will have a step here. 2 pi over n. So what we have here is definite integral. Very convenient. Definite integral from 0 to 2 pi of p over theta d theta. And now let's transport this to a more convenient place by the function p, so we can actually see what we're doing here. We can bring out 2 over pi, so that's gonna cancel out, and that's going to be a definite integral from 0 to 2 pi of p of theta. That's just gonna be okay, we brought out the 2 over pi. Oh wait, no, it's not like entirely like that. Okay, part is in the denominator, part is in the numerator. So 2's are gonna cancel out, and we're gonna have 1 over p squared times the definite integral from 0 to 2 pi of absolute value of sine 2 theta d theta. Now we can kind of partition it into segments, sort of. So let's do precisely that. So let's look into 0, pi over 2, pi over 2 to pi, from pi to 3 pi over 2, and from 3 pi over 2 to 2 pi. So in this part, sine to theta is gonna be positive. And this part is gonna be negative, positive, negative. And now thing is, sine some sort of x plus Pn, and then we take the absolute value, it's just gonna be sine of x. That's really handy. That means that we can rewrite this definite integral essentially in a different form. We can write down this as 4 over pi squared times the definite integral from 0 to... Okay, I forgot to mention, for this x is supposed to lie from 0 to pi over 2. Okay, let's use the square brackets. Okay, now the thing is, we can cut the entire domain like that, not the main bounds of the integral, from 0 to pi over 2, because we know that these sections are essentially going to be equal under the absolute value. It's really handy, because now we can get rid of the absolute value here and get just a proper, adequate integral expression. So let's do a substitution. Have 2 over pi squared times definite integral from 0 to pi of sine theta d theta. And now it's a really simple integral that everyone knows. 2 over pi squared times the difference minus cosine of pi plus cosine of 0. And we know that to be 2. So what we have in the end is 4 over pi squared, which is a pretty interesting result. Can be rewritten as 2 over pi squared, like this. So that's it for today. I want to leave a message. This channel is not really educational in the classical sense. It doesn't educate the viewer. It educates the person recording the video. So if you see any sort of mistake, or if you want to add something, then feel free to comment. I'm going to read it, and I really just want to learn in the end. Thank you for your support. Thank you for comments. Thank you for ideas and inspiration. That's it for today. Bye.